Hello everyone. So this is, you guys should have already completed your timeline, and we are now going to do the notes for this section. Now starting off, remember you only have to write things in the notes section that is highlighted or that is underlined, and I will also tell you as well. Okay, today your topic is history of atoms. Your goal is I can point out important people and events that happen in the history of atoms and the periodic table. So to start off, I'm going to ask you guys a question. What is similar between a blade of grass and the sun? Well, we know they both are made up of atoms, and of course, they also have other similarities as well. So in your notes section, atoms is the word that needs to be highlighted, and the definition is the building blocks of matter, or basically they make up all matter. And this is what we're going to kind of start off talking about today, is the history of atoms and the history of the periodic table. So, early ideas about matter. Back in the day, Greek philosophers thought that matter was kind of like an episode of Captain Planet, like earth, fire, wind, and water, also kind of like Avatar. And basically that's it, and it can't be broken down into smaller particles. Democritus, which is highlighted, so you need to make sure you put that in your notes section, was the first to say no, matter can't continually be split up. He also said atoms are solid, homogeneous, indestructible, and invisible. So that part that's underlined is all you need to know about Democritus for these notes. He thought they had different sizes and shapes, and those characteristics determine the properties of matter. Okay, also kind of a little tip. I'm not going to necessarily stop for you guys to type. Since this is a video, you can pause it, type it, and then restart it right back where you are. So I am going to kind of keep going at a pace, knowing that you can pause the video. All right, the next person, Aristotle, which is red, so make sure you highlight him, said that atoms could not move through space. Now, he said that because he just didn't believe that free space was possible. Aristotle was more popular, so everyone rejected Democritus's idea and went with Aristotle, even though we know Aristotle was wrong. All right, so in this picture, can we find similarities in this work and Democritus's ideas about matter? So if you look closely in this painting, you'll notice this painting is only made up of dots, and each dot comes together to make an image. So this kind of shows what Democritus thought an atom was, were these dots that just come together to make up everything. All right, next person we need to know is Dalton. So basically, Dalton was this super smart dude, dropped out of school at 11, but came back to be the teacher at 12, and then since Democritus was not able to do any experiments on his theories, Dalton is the one who conducted the experiments to prove or disprove Democritus's work. So he found some different things to be true in his experiments, and that is matter is composed of small particles called atoms. Atoms are indivisible and indestructible. Atoms of a specific element are different than those of another element. Different atoms combine in simple whole number ratios to form compounds, And in chemical reactions, atoms are separated, combined, or rearranged. Now, Dalton was on the right track, but there was a couple things he got wrong in his theory. And one is he said that basically atoms cannot be divided any smaller. Well, come to find out later we can, and we'll talk about, and that's the nucleus with protons and neutrons, and then also the electrons. And then he was also found to be wrong about all elements of the same kind having identical properties. All atoms, even of the same kind, are also found to be different in their masses. The mass that we see on the periodic table is actually an average, so he was kind of incorrect about that as well. All right, that brings us to the next person. So Sir William Crookes saw a flash of green light in something called a cathode ray tube and got excited while inventing the Crookes tubes. But J.J. Thomson set up the cathode ray tube and found subatomic particles with a negative charge, which is the electron. So make sure you write down J.J. Thomson and then the definition or what's underlined after that, and highlight J.J. Thomson. So here's a picture of a cathode ray tube that was used. And basically, it's kind of like a battery with an anode and a cathode, or a positive and a negative end. And then it has a glass tube with alligator clips. And this tube is what was used to find the electron. Okay, so Thomson had a question. He wanted to know what the mass was. He knew that it couldn't be an atom because it was smaller than the smallest atom. So he knew it had to be a subatomic particle. And then he came up with this model called the plum pudding model. So you don't need to highlight that. You just need to write down plum pudding model. And this is the model that looks like a chocolate chip. So basically you have your cookie, and then the chocolate chips would be the electrons, and the cookie is the nucleus itself. All right, next we have Ernest Rutherford. So make sure you write Ernest Rutherford and highlight that name. And he did something called the gold foil experiment. So basically that experiment determined that almost all the atoms' alpha particles were found in the center in a really dense region, which he called the nucleus. And then he also, that positive center is the protons in the nucleus, is what he found. So he also determined the relative size and density of the atoms. The experiment discussed the neutral charge of the element, with the positive and negative charges canceling each other out. But it still did not explain the total of the atom's mass. So they knew they were still missing something, but they didn't know what they were missing. And that brings us to James Chadwick, which it was Rutherford's coworker. So you need to know who James Chadwick is. He found the neutron, which had a neutral charge in the nucleus as well, and he won a Nobel Prize for it in 1935. Okay, so completing the atomic model. This is a lot of words, but basically what it's saying is the electrons orbit the nucleus that is made up of protons and neutrons. And protons and neutrons make up 99.97% of the mass, which means electrons are very small and very light. And then they also found out that there was something smaller than a proton and neutron called a quark, which we'll talk about in just a little bit. We also know that chemical reactions only use the atom's electrons unless if it is radioactive. And then we now use and accept the electron cloud model. So you need to type that in your notes, just electron cloud model. And here's kind of a picture of that. So basically you have your nucleus, and then these electrons are like floating around in this cloud, and they're in different orbits. And the different orbits tell you where they are. And we will talk about this when we talk about electron configuration and what orbit, how far from the nucleus electrons are. All right, so now we are going to jump into the history of the periodic table. Henry Moseley, important write him down, highlight him. Discovered that every element has a set number of protons found in its nucleus, and from this he created an atomic number. This number represents the number of protons in the atom's nucleus. And every atom is neutral, meaning there is the same number of protons as electrons, so there is no charge. Lavoisier, highlight him, type him down, make sure you got him. He started the modern day periodic table, but only lists 30 current elements. That's all they knew. But later, after electricity was introduced, they were able to discover many more, because electricity means there are instruments that use electricity, which means there are other ways for them to find elements. By the 1870s, there were 70 known elements. Okay, so a need for chemistry. After the Industrial Revolution, manufactured goods took off, which means they need to know how to make items fast, cheap, easy. So they hire chemists to come in and figure out what the cheapest material, the cheapest elements, the way they can make the most money from it. So that helped make people study chemistry, and we were able to find more information out because people were studying chemistry. So the beginning of the periodic table, the push of chemical understandings led to a push for a periodic table which described how they would react, what they will make, and what the reactions are, which we know reactions are caused by the electrons. Okay, so that brings us to John Newlands. Okay, so highlight him, underline him. He arranged the elements in order using the element's atomic mass, and noticed that properties repeated themselves every 8 elements. Well, the fact that it repeated every 8 elements is also known as the law of octaves, which you need to have typed and highlighted. Okay, so here is his first periodic table. It doesn't look like ours, but it's the first step to get where we are today. So the flaw. It didn't hold for every known element, and for some reason the scientific community did not like the word octave, so they didn't really accept that. And then basically it was saying he was right, he just was off on the specifics. Like he just needed a little bit more information. Which brings us to these two people, Mayer and Mendeleev. So basically, they found, just as Newlands, that if you arranged it in atomic mass, elements had certain similarities. They left them in columns or groups to represent their chemical behavior. And then also, by doing this, Mendeleev was able to predict unknown elements. Now, we know all of them. The most recent one being the tennessine element, which kind of filled in that last square on the periodic table. But they were able, even though they've never seen it, they've never made it, they don't know these elements, they were able to predict them based on the patterns of the elements they've seen. Okay, next person, Henry Moseley. So highlight him, type him down. He rearranged the first periodic table and used the atomic number instead of the atomic mass to create the modern day periodic table that we use now. Because you'll notice there's a couple of spaces where the mass is actually smaller after, like it's opposite order. But putting it in the atomic number order, it made it complete and correct.